So once again, welcome everyone to this webinar. And as you know, we have been talking about this similar topics for a while. And I think it's important because sometimes the traditional design that we are so used to fails to give us the in-depth information that we may require in certain cases. So today we are going to once again focus on the moment curvature curve, and especially with respect to the capacity calculation using the capacity design procedures. So let's begin once again, and let me start with this. From the top, we have seen this equation before also, because one of the role of the structural engineer, as you know, is to reduce the disaster due to natural hazards. And as you know, hazard, vulnerability, and exposure combine to contribute to a disaster. And out of that, the hazard is natural, sometimes like earthquake. We don't have much control on that. Exposure is due to planning and optimization and other development, which often sometimes beyond our control. But the main thing that is structural engineers control is the vulnerability of structures. So our intent, or the intent of the design codes and the design, is safety. Safety in terms reduces the vulnerability, and in turn it is going to reduce the risk to disaster. So if we want to reduce the risk to disaster, the one thing that we can do is to make the structures less vulnerable or more safe or high performance. And that's what we are talking about. So hazard normally translates to demand. For example, load effects, earthquake loads, wind loads, and others. And normally they are ultimately transferred into bending moment, shear forces, and things like that. And vulnerability is related to capacity. So if we somehow improve the capacity, then we can reduce the vulnerability and obviously then reduce the risk for disaster. And that's what we are talking about. And the capacity, we are going to talk about two kinds of capacity: the strength capacity, or the traditional capacity from the code-based design procedures, and the enhanced capacity for deformation and so on that we can compute using other techniques. So let's get into that. Vulnerability, capacity, and everything about a structure is in a hierarchical system where it starts from materials. So we can see the importance of the material response, to the cross-section response, to the member response, and finally to the structure response. And any steps that we take along this ladder will affect the steps above them. So which means that to make these structures, we have to start with the materials and cross-section. Today we will talk about the materials and cross-section combined together to give us the strength as well as the performance. So normally for the design codes to add safety in structures and reduce vulnerability, it's an implicit way to do that. And they normally use it by controlling the capacity to be always more than the demand, so that the vulnerability will be less. And with some factor of safety, obviously, as we are familiar with. So now this DCR, or the demand over capacity ratio, is one of the primary indicators for the design to be okay or design not to be okay, acceptable or not acceptable in the traditional sense. So normally we have this idea that there is a single number of 1, and anything which is on the left side is safe, and anything on the right-hand side is unsafe or is vulnerable, and what is safe is not vulnerable. And we typically draw the line at the demand capacity ratio of 1. That means the capacity always being more than demand or just equal. But we will see that the calculation of the capacity has many levels, and we will look into these today to understand how they affect this equation. So now if you look at the demand side, to calculate the demand, that means, let's say we're talking about bending moment, applied and bending moment capacity. I'm using the ACI kind of notation, for example, MU and MN and phi, but other codes have similar concepts as well. So let's say for the demand, it will travel a long way from the load patterns to load cases to analysis to calculating the forces, then load combination from those four basic forces, then action envelopes and design action sets. And then we reach the final design moment, or MU. This has already been factored through several layers. This number is not real because it has been factored and combined through with other cases and combinations and so on. So this is not a unique number that represents any physical quantity. On the other hand, the capacity also starts and with the materials moves to sections. Then theoretical capacity we calculate through theoretical computations. Then we modify this one by the design capacity equations, which is reductions for the capacity reduction factors and so on, in phi in this case and gamma in other codes. So then we compare them together. So as you can see here, neither the moment, mu, nor the capacity are real. Both of them are kind of indicative numbers going through the process, and the intent is that they are ultimately going to make our structures safe. But both of them are unreal in the real sense. They do not represent any physical reality. So material plus section capacity, let's look into that in a little bit more depth and see how they are computed and see where are the code factors, where is the theory, where is the real, where is not the real. Okay, so when we talk about the cross sections, and the discussion today will focus on beams, beam cross sections, various type of beams. It will focus on columns cross sections, various types of column cross section, including composite and reinforced and so on. And it will also be applicable to shear wall sections, both composite and the reinforced. So we are talking about cross section of these primary structural members, columns, beams, and frames, not including slabs in this discussion. And these cross sections can be of varied shape depending upon the structure. If it's a bridge pier, it can be like that. Shear walls will be like that. And then even confined, the green ones that you see here, they are the confined columns coming from AASHTO and other Caltran agencies, which use special type of reinforcement patterns to create their bridge piers. So we can see here that it's a large variety of cross-sectional shapes, configurations, and materials that are used. So now the question is, can we develop a unified equation to compute the basic capacity? And I'm talking about now axial flexural capacity. I'm not talking about shear at the moment. So let's talk about the one of the primary concerns is, or primary source of structural performance is the axial flexural capacity. So if we do look at that, then if we think about a cross section which is partially pre-stressed and is composite, and use that as the basis for developing our theory, then it can cover all the cross sections that we have seen in the previous slides. So that means if we develop the theory and it's applicable to this one, then we can solve all of the cross sections of columns, beams, and walls. So that cross section is represented here as a kind of an idealized section with a steel section inside, reinforced concrete shape of any shape. This is subjected to a curvature as well as axial force. That means we have a strain distribution and a corresponding stress distribution in concrete and steel section. So this is basically a typical stress-strain equilibrium state of a cross-section under combined deformation of axial and flexural effects. So if we take that, then we can see that it is coming from two components, axial force and bending moment. Bending moment may be subdivided into moment about x and y, or moment 1 and 2 and 3 and whatever we call it, but ultimately it's a resultant moment that we are concerned with about a particular angle. So this combined will create a state of stress and strain that we have seen earlier. So let's start step by step. The first one is, let's look at a column which is only subjected to axial shortening. So we have an axial shortening, this one caused by any reason, load or otherwise. If there's a shortening here in the cross section, which is the reinforced concrete cross section, then if we limit the strain for this shortening and say, okay, this specimen or this column cannot deform axially more than 0.003 strain, can we calculate the capacity at that limiting strain? This is an arbitrary number, but let's say that is the number that we are going with. Then Based on that, we can go to the concrete stress strain curve and steel stress strain curve, and we can calculate the corresponding stress for the strain of 0.003 from each of the material stress strain curves, bring them into this equation, and then we have FC, and then we have Fs multiplied by area of steel, multiplied by area of concrete, and then we have the total axial capacity or axial capacity stress resultant. This is what we are talking about, is the strength capacity. So that means this is the capacity of this column to carry this load P for a failure strain of 0.003 based on the section's configuration and material properties like that. We can repeat the same thing for a beam under curvature. Let's say it is under bending and then it is curvature. So it basically has a non-uniform strain and we have a curvature. In this one, same thing, the curvature will produce concrete stresses in some portion and zero stresses on the other, or negative small tensile stresses and stresses in steel. And using the same concept, we can extend the same way. We can look at the strain for 0.003 and then corresponding stress, and the same for the steel, and then we can assume that this is an equilibrium, no axial load. Then we can create this, we can write this equation for the bending moment capacity, once again the same way as for that. And this becomes the moment capacity stress resultant, which means that the axial force capacity and moment capacity can be determined from basic cross-section, shape, size, reinforcement, and material properties for a given strain level. And this is what is normally termed as the strength capacity that we use for the DC ratio checks. So for a generalized cross-section with two moment components, we can expand that into integrals for a general shape. So we can write this integral. Basically, it's the same. It's a stress resultant, adding up the stress due from concrete and bars and the moment arm for each of the small area on the cross-section and multiplying them to compute the total moment. So this is how you can calculate these three components of the capacity. Now, what is very important to note here is that these three components form a set. They exist together for any stress strain configuration, any deformation strain. They are not independent, they are dependent. If you change for example, the strain level, all three will be affected. If you change the material properties, all three will be affected. And because they are dependent, they have to be treated as an interaction and they have to be treated together. So now there is no single axial load capacity, no single moment capacity, no single MX capacity. They are all together as a set. And this creates another level of difficulty in defining what really is the strength capacity, because now you cannot define them independently. So these three equations actually lead to the plot shown on the right-hand side, which is the typical axial load and moment interaction plot. And this is an interaction surface or failure surface, which is generated by setting the strain to be 0.003 and solving those equations on all angles around that. In fact, this can then be cut along the vertical and horizontal axis to generate two curves. One is the PM curve, which is interaction between axial load and bending moment about any direction, and the MM curve, which is interaction between moment about one axis, moment about second axis for a given axial load. So these are the final tools which we can now use for the purpose of checking the DC ratios. Still, there are many problems here, but let's not go into them right now. So we have these interaction diagrams. Now, let's look at how this interaction surface is generated. So basically, you take a cross-section and you vary the neutral axis depth. For each variation of neutral axis depth, we calculate the corresponding strains, we calculate the corresponding stresses, we integrate them, we calculate the P, M and M1 and M2, we plot them on this side, and we keep rotating the cross-section for every possible angle of bending. And for each possible angle of bending, we once again vary the neutral axis depth to get various levels of P and then corresponding levels of M2 and M3. So when we complete this rotation of the cross-section 360 degrees and all variations of neutral axis for a given strain value of 0.003, we are able to generate the full interaction surface. And that becomes our main tool to design the cross sections for strength. Now, please note that this interaction surface, as we call it, is a property of the cross section, unique property of the cross section for a given strain limit. If you change the strain limit, this will be different. And this is, we can generate it for any cross section. So having done that, we have the basic tool. Now, let's see how does it compare with the traditional code method or simple formula that you might have seen in the books, or you might have used. A simple rectangular beam actually gives us this simple formula of the moment capacity on the left-hand side. It is the same as this equation for this one. Both of them are identical, only difference being that one is generic and general, other one is very specific and very limited in terms of its application. So the two equations at the top and the bottom are identical in concept. So both of them are representing the capacity of a cross-section, one a moment capacity, other one all three capacities simultaneously. So these are not equations for design of section, because the cross-section has to be known, reinforcement has to be known before we can compute this capacity. That means it's a capacity check. It's not a design. So to use it in design, we actually need to use iterative procedures to check the capacity and see if the DC ratio is not right. If it is right, it's okay. If it is too much, we reduce reinforcement. If it is too less, we increase it, and so on. So we utilize these equations by, as I said, using them as tools for capacity check. So basically, we compare the section response with the cross-section action determined from the analysis, like I showed you earlier, MU versus phi MN, or PU versus phi PU, and so on. So we can do that from this comparison. But the problem is that now we haven't talked about factor of safety. How much DCR should be, how is calculated, and where is this factor of safety inbuilt by the codes? So the strength should be more than action, but how much more? And this is where many codes will disagree, or will be differ from each other. So let's look into that. So the concept of factor of safety was introduced long time ago due to many reasons. In real world, the cross-section capacity should be just enough to resist actions, but practically section capacity should be more than actions for multiple of reasons, which I don't want to discuss now. But let's say that we have to have a certain factor of safety. But the question is, how much? And then this factor of safety is the one that we should now include in our theoretical calculation of the capacity equations. So that DC ratio that you looked at, MU and phi MN, we now put a phi factor to reduce that theoretical capacity by a certain factor, and also increase the MU by a certain factor. So intent of the code is very clear. They want safety. They also want simplicity, and they want statistically reliable outcome. So because of all of that, the factor of safety is to simplify, also to ensure safety and make sure that statistically we are doing the right thing. So that is done by either dividing the strength, or by multiplying the loads, or by doing both, dividing the strength by a factor and multiplying the load by a factor, called partial factor of safety concept. And that's what most codes use these days, modern codes use. So to do that, the codes have to simplify things, because full equation that I showed you are obviously very complicated. So they will simplify the material models, they will reduce the material strength, and they will also reduce the capacity values directly, so that they add factor of safety on those three ways. So let's see how they do that. For material reduction related factors like Eurocode, BS code, Indian code, and other codes derived from there, they will normally use a gamma factor to modify the strength of the material. For ACI, Canadian, and other codes, they will they will decrease the capacity directly by a phi factor. So if we include both these factors in the equation, then these equations that we developed earlier become universal, and they can be modified to handle any design code, either by modifying the material components or by modifying the entire resultant. So both these can be used. So that means the codes will use any of these things to modify these capacities. And this is factors from the codes. You can see here ACI and other codes. So these factors could be 0.85, 0.7, 0.9, or in case of the Euro codes, it could be gamma could be 1.15, 1.5, and so on. So we have those mechanisms to modify the strength to be less than the theoretical one. So this is what happens. The blue line outside is the theoretical strength calculated from the equations. And this is reduced to that orange line by the design codes by including those factors that I mentioned. So you can see there's a huge reduction, especially on the compression side, because of the brittle nature of the failure in compression. There's a larger reduction on concrete side and a smaller reduction on steel side. So you get this reduction. And then from the ACI 31821, if you look at their own description, they can see that the theoretical value and the reduced value is very different. And this is an additional factor of safety that has been added. So the acceptable region becomes quite small compared to the theoretical value available. So now let's get back to the design of a structure. Let's say we are supposed to design a frame like this. Then, like I mentioned, we will define the loads and load cases, analyze the frame, get the design actions, applied load factors and combinations, and then we will use DC ratio less than 1 to determine reinforcement and check capacity. And that's how the design code will work, as you know, for the capacity-based design. But the problem is that if the capacity is, the load applied is inside, we consider it to be safe, that point here. And if it is, and then we can draw a line connecting that, and then we can, let's call that length, let's say a vector, and then we can call the capacity, true capacity, or the code capacity as C, and this as demand. Then we divide those two, we can get the demand to capacity ratio. And we can see here that they can result in different interpretation. Demand capacity ratio for moments may be different from demand capacity ratio for axial load and moment, because their vector have a different meaning. So now we have two definitions of demand capacity ratio, one DC ratio at a given load level and one DC ratio at a given bending direction. Both may not be, in fact, most cases, they will not be the same. So we can already see that we have a different definition of the capacity. No single number is now clearly valid. So these are some of the limitations that we have seen, that first of all, they represent one unique value on the strain, and also they are modified by many factors, and there is no unique definition of the capacity for a typical interaction of the axial load and bending moments. And coming back to this one, if this point of the demand is inside, is safe, this point which is between the code and the theoretical, actually this is not unsafe, because it is still less than the computed capacity, but just more than the code capacity. So now the question is, should we accept this number or not? What is the state of the structure here? Because right now it's just an arbitrary reduction, and different codes have different reductions. So some codes it will pass, some codes it will fail. And then this number, which is outside of this demand combination, which is completely outside the theoretical, is considered to be unsafe, both for code and for theory. But this is only unsafe if the strain of concrete is considered to be 0.003. But actual strain capacity of concrete is actually not 0.03. It can be much larger. So that means this capacity based is not very useful when we talk about the real state of the cross section and real available capacity. So let's move on. Now, so if you look at a structure, then normally for the design of a structure, we are looking at several aspects. we are looking at stiffness, stability, strength, ductility, damage, stress strain state, what is the strain or state at any location, damping, and energy. These are the factors that normally are, you can say, performance indicators. And the strength equation only gives us one of them. And that too, not exactly. That is also quite arbitrary because the load is not real, capacity is not real, so the comparison is not real. So if we want a reality check on these indicators, then strength equations will not be very relevant. Okay, so this is just a table showing that the strength equation does not satisfy or does not help in determining most of these parameters directly. Okay, let's go to a simple example now. Let's say we have a beam and we want to answer these questions. The beam is already constructed, somebody designed it, we built it, and now I see what is the maximum load this beam can carry? What will happen when it reaches the maximum capacity? When and where it will crack? How much will it deflect? Will it fail in shear or bending? Can I control how it fails? What is the most efficient way to size it? And so many things. Unfortunately, our design DC ratio does not answer any of them because they are based on theoretical, unrealistic numbers, both of which are not relevant to the question that we are asking. For example, if you look at this beam, same beam, similar beam, and we have two loads, if we increase the load from 0 to maximum, you can see the bottom line here, the beam will deflect in a non-linear manner, not in a linear manner. At some point, it will start to crack, then deflect a lot, then damage a lot, and finally it will break. But the capacity equation and interaction diagram on the right only gives us the condition when this moment has reached the theoretical ultimate moment. Not all the moments when the beam is going through this deflection curve. So that means it's just one point on that curve, and that too not real because it is based on factored load and factored capacity, but the actual load applied here, F, is not factored. So we can't really get correlation between real load and the capacity diagram that we have here. So theoretically, it may be here one point, but actually load can vary along this one at any location. Moment can vary from 0 to any moment, and all of them will exist until the beam really breaks down, assuming that it doesn't fail in shear first. Okay, so let's get back to the frame now. So and look at the same questions on a frame. Now this frame looks like concrete, but if you look at that, actually the frame has reinforcement inside. Confinement, stirrups, ties, vertical reinforcement, horizontal reinforcement, and many things. So that means now the capacity of this structure needs to be calculated not as a concrete structure based only on concrete section, but on the actual reinforcement that was provided and the actual details that were followed. So if we want to answer all these questions for this frame, then we have to go beyond the capacity calculations. So now, and the reason is very clear. If you look at the column that I take out from that frame, and then you calculate the load, actual load on the column, P1 and M1, let's say, and then we bring that load onto the design side, we have to multiply them by some factors, some load factors, LF, and then we multiply them to get P1U and M1U. Then the capacity that we generated for that strain of 0.003, which is an arbitrary strain, we have reduced them to an orange value by capacity factors. So we don't know what is the strain at that orange level because we only know the strain at the blue level, which we use to generate that curve. But after we reduce the moment curve, the strain is not known at that red curve. Also, we don't know what is the state of the column at the actual loading because this is already factored. So which means that the strain capacity cannot answer the question of what is the strain at the load P1 and M1. And that is the starting point of many questions. So which means for evaluation of a structure, the strength equation does not give us any information because it's based on arbitrary orange line and arbitrary loading pre-multiplied by load factors. So for real load, real stress and strain information cannot be determined from this one. So then how can we do that? We can either test the beam physically, that's one way, and measure all the strains, which is good, or we can simulate the behavior through computations. So let's look at that. Let's say we test the beam, and this is one of the examples. So this is the test of the beam in AIT, one of my class, and you can see that when you test the beam, you can actually observe the deformation, you can observe the cracks, you can observe the strain, you put the strain gauges everywhere, you look at the cracking, you start measuring everything, you just start noticing what's happening, and then you can observe the first crack, for example, you can note down the load against that first crack, and you can continue to observe the failure or the behavior of the beam until it completely breaks down. So we can get the entire history of deformation of the beam together with the cracks, spacing, location, and thickness, and so on. And we can plot this curve between the load increase and the deformation, and we get this nonlinear load deflection curve. And this nonlinear load deflection curve is coming from moment deflection, which is nonlinear, which is coming from moment rotation, which is now also nonlinear, which is coming from moment curvature, which is also nonlinear. That means we have everything, all the relationships in deformation are nonlinear. That means our strength equation, which is based on one unique strain, is not going to help us in any of this. So that means we need to look at the moment curvature as a starting point if we want to go to moment rotation, and from there we want to go to moment deflection and then load deflection. So that means starting point must be moment curvature if we want to use computations and reach the same results. And that's where we can do. And that brings us to moment curvature. So the relationship between moment and curvature has been understood for a long time. Moment is equal to stiffness multiplied by curvature. If you integrate curvature for a small distance, you get rotation. And if you integrate it over the greater length, you get the deflection. So the only thing which is stiffness oriented or stiffness related to moment is the curvature. Curvature to rotation is geometric, and rotation to deflection is also geometric. So deflection, in fact, has no direct relationship with moment. It is related to rotation. Rotation has no direct relationship to moment. It is related to moment through curvature, which has a direct relationship to moment through stiffness. So that means if we are able to determine moment rotation relationship, we can determine other things easily. And that's what we are talking about here. So this is the linear interpretation of this one. But we have seen that this is a nonlinear problem from the testing. So we can see from here that the curvature is actually rotation of the neutral axis and the deformed cross-section, and it can be measured or defined in many ways. It can be ratio of the strain over the neutral axis depth or equivalent depth. It can be measured in terms of the strains and so on. So, or it can be measured from the radius of curvature. So you can define curvature in many ways, and these are all very useful relationships for us. And this curvature can then be related to moment and also axial load, because axial load can modify this curvature, either increase or reduce it. So now we have a nonlinear moment curvature relationship. So curvature is a slope. The stiffness is the slope of the moment curvature diagram, and curvature is a ratio between moment and stiffness. So how do we generate this moment curvature curve? Actually, we use the same equations that we used for capacity calculation, just a slightly different algorithm is used. So basically, we use the same equilibrium equations, same formulation, same everything, because we are still talking about the stress resultant equilibrium in any case at every stage. So we use that. The only difference is that for moment curvature, for PMM diagram, we fix the strain 0.003 and we vary the neutral axis depth as you saw in the video. For moment curvature, we vary both strain and neutral axis until we find the equilibrium with axial load, and then we find the corresponding moment, and then we generate this one. So this is an iterative that is straightforward. So moment curvature curve may not always converge, but we use iteration to find the equilibrium between axial load, applied axial load, and internal stress resultant, and the moment corresponding to that. So that's how we basically generate this one. So what are the things that affect this moment curvature curve? If this is a moment curvature curve, this curvature curve is affected by, first of all, it is affected by the angle of bending on the cross-section, because moment direction will be important, because cross-section has different behavior in each direction of bending. It is also affected by the axial load, because the equilibrium is calculated for the given axial load. It is also affected by the cross-section size, shape, reinforcement. It is affected by the concrete stress-strain curve and the steel stress-strain curve. Now, out of these, one of the important one is concrete stress-strain curve, because this can be modified or this can be affected by the confinement of the cross-section. So that is something that we can look at, because that can give us a tool to modify the stress-strain curve without changing other parameters. So basic material stress-strain curve is like this, that is steel, that is concrete. But if you put the concrete on the same scale as steel, you will see that concrete is a very small component in the stress-strain diagram. So it seems so small compared to steel that it is almost invisible. But because of the large area of concrete, this becomes significant. So if you look at the cross-section or look at the column or a specimen of concrete, when you compress it by P, because of the Poisson's ratio, it will expand and it will fail because of the tensile stresses produced, which are parallel to P, and then it will break along that. So if we can somehow prevent this expansion of concrete, then we can increase the ductility, and also we can increase the axial load capacity. And that's the idea behind confinement. So if you confine the concrete like this one, then you can increase the stress strain ductility a lot, and the capacity, axial load capacity as well. And this is a great tool to modify the moment curvature curve. So you can see here, if you have a column with no confinement, moderate confinement, heavy confinement, and very heavy confinement, then the stress strain curve of concrete for each one of those columns will be different. And this is something that is not reflected in the capacity design equation, because capacity design equation only takes into account the longitudinal steel ratio and does not take into account the transverse steel or ties into equation. It's just when we generated that, we did not consider the transverse reinforcement. But moment curvature does, because we modify the stress strain curve by confinement. So unconfined, lightly confined, heavy confined, very heavy confined, and extremely heavy confined concrete sections will give us very different concrete curve. Now you can see here that the failure strain of concrete is as high as 0.05 or 0.04, not 0.003. So confined concrete can take strain much larger than the capacity strain that we use. That means actual sections, column and beam both, have a much larger capacity than was predicted by the strength equation, because that was based on a strain of 0.003. So I mentioned earlier that axial load has a relationship with the moment curvature, because the equilibrium and because compressive load can consume most of the concrete capacity. So when your compressive load is increased, the curvature capacity reduces. So as you increase P, curvature capacity reduces. And this is a plot that you can see, and you can compare it with the PMM diagram. So right-hand side is an interaction diagram between axial load and two moments. Left-hand side is a diagram showing interaction between axial load and the curvature in two directions. And you can also see that the curvature heavily depends on the direction of bending. So as for the right-hand side, you can cut the diagram to get PM and MM curves. The left-hand diagram can also be cut to get the axial load versus curvature relationship. and curvature relationship for different angles of bending. So now, moment curvature can help to determine more response parameters because it can help to determine almost all the parameters on this list. Not only strength, which can also be determined from moment curvature because it is the moment at the yield point, which is the strength. So you can see now that moment curvature has given us the capability to get more insight into the structure. So you can see that almost all items now can be computed directly or indirectly through moment curvature, using moment curvature and its derivations, for example, rotation and displacement. So now the PMM diagram could not answer the question, what is the strain at P1 and M1? Moment curvature curve can answer that question easily because now the curvature for the corresponding moment M1 can be determined from that curve. And then at that curvature, the state of the cross-section is known because we know the strain, we know the stress, we know everything, which means that the curvature for a given moment and given axial load can give us complete state of stress and strain and everything else that we need for a cross-section. So this is very different for strength, and this we can do for any level of moment and any level of axial load without multiplying by any factors for load and without dividing this by any code capacity factors. So this is almost real versus real. So what can we get from curvature? We can get many things. We can first of all get the stiffness. We can find the stiffness. For example, if this is the gross stiffness, then from the moment curvature, we have two materials. When we combine them together, we get the crack cross-section for a particular moment, and we can compute the stiffness from moment curvature, and we can then compare, we can get it for different moment values or different curvature values. So we can get the initial stiffness, starting point, we can get the secant stiffness, we can get the tangent stiffness, and we can get them on any location. And this is one of the key strengths of moment curvature because it can be used to generate the moment rotation, stiffness, and so on. So we can use these numbers to carry out the analysis, which I will show you in a few minutes. So we can also calculate the yields rotation, the maximum curvature, yield curvature, ultimate curvature, ductility ratio of curvature, and so on. We can also use the cracking moment, yield moment, ultimate moment. This is the true ultimate moment, not the theoretical one, ultimate moment capacity, and ultimate curvature moment capacity, residual moment capacity, and so on. So we can determine so many things on the curve. We can also determine the immediate occupancy for performance-based design based on a limit on curvature or limit on rotation or limit on anything, so or strain. So we can, based on that, we can put those limits here. Immediate occupancy, life safety, and collapse prevention can all be located on moment curvature curve. So as you can see, from basic stiffness calculation to all the way to performance indicators can be located on this curve. And we can see, if you just play this one, you can see, if you look at the moment curvature curve, when you move the cursor on that using CSI call, you can see the variation in, let's say, concrete strain for any location. And you can see also that how it will vary. Similarly, you can see the concrete stress for any location on the moment. So this is the cracks location, the tension concrete is gone, compression stress can be calculated. You can see from there, and when you move that, you can see that now the concrete is gone on the top, and the concrete section is just only steel is left. So all of that behavior can now easily be determined from the moment curvature curve. There are so many graphs that you can plot, and then so many insights that you can get. So this, using CSI call or programs like that, you can actually determine the stress strain of the cross section at any moment and any axial load in any direction. Same is the case with steel reinforcement. You can find the stress and strain in steel the same way as in concrete. It's just a matter of plotting these values onto the for a given moment or given curvature. And more importantly, you can also study the effect of confinement. So this column has a confined zone and an unconfined zone outside. So you can see the difference when the concrete cover might fall and when the concrete cover will be gone and when the core will be acting. So if you take a look at that, both of them are acting. At some point, you will see that the cover is now gone, but the core is still present. So you can see how the core continues to provide compression while the cover is gone. And this is a very important insight that we can get, and we can see the state of the cross section for these behaviors. Similarly, we can look at the stress diagram in 3D. Same thing. We can plot how the stress will vary as the moment initially it is linear, and after that it becomes nonlinear, corresponding to the stress strain curve. This is the stress strain curve. The outside stress strain curve is different. Inside stress strain curve is different. Confined is different. Unconfined is different. So you can see that we have a very detailed response determination for the cross section if we rely on moment curvature. And similarly, for the angle section, you can see that when you bend the column on a 45-degree angle, the corner will break very soon, and the column will lose the curvature capacity rapidly because the concrete on the corner is very small compared to the edge. So we lose the capacity very, very, very quickly. So we can determine concrete cracks, we can concrete first yield bar, we can look at the concrete crushing, we can look at the residual strength. Everything can be plotted on the moment curvature curve if we have sufficient information. So because now we have curvature, we can determine the rotation and we can also determine the deflection. And that's one of the biggest application of moment curvature, because curvature can then lead to rotation, rotation can lead to deflection, and rotation can also lead to stiffness used in nonlinear analysis, because we can create moment rotation hinges that we can use later. We can also determine the crack spacing and crack width because we know the strain, and if we fix the crack spacing, we can determine the crack width and vice versa. So this roughly shows you that moment curvature can determine so many quantities: stiffness, deflection, rotation, slope, strain, crack width, and many things that we talked about. And we can continue. We can determine neutral axis depth, concrete force, steel force, and so on. Another important thing is that we can also determine now the energy, because we have the full curve. So as you know, area under the curve will give us the energy. So we can determine the strain energy, both elastic and inelastic. And we can also determine the curvature energy, both elastic and inelastic. And this will help us later to determine the energy dissipation and to estimate how much energy the structure has stored during deformation. So the ductility levels can go from strain to curvature to rotation to deformation. Energy levels can go from strain to curvature to rotation to deformation. And similarly, the whole structure, now we can do the nonlinear modeling by creating a moment curvature curve based on the material's stiffness, which is nonlinear. Stress strain curve goes to moment curvature curve, moment curvature goes to moment rotation curve, and moment rotation curves to load deformation curve. So now we complete the cycle or complete the story of how moment curvature curve based on stress strain curves can lead to the structure's deformation, nonlinear deformation computations. So we can build up the stiffness, ductility, and energy in that concept. So let's look at final topic in this discussion. How can we use this curve in seismic design? We have already put all the pieces together. Let's apply it. So this is a schematic of how the stress strain curve from material combined with cross section gives you the curvature, moment curvature, which gives you moment rotation, which is assigned to the plastic hinge, which when done a pushover gives you the ability to calculate pushover, and from the demand side, seismic response spectrum can be converted into ADRS, and then we combine them together and we can find the performance point, IO, life safety, and so on. So this is the conceptual framework which we can see the importance of moment curvature in determining the seismic performance. And you can also use it for nonlinear analysis, time history analysis. Same, you can combine it with realistic site-specific hazard analysis and realistic performance evaluation. But the basic tool remains the moment curvature curve, either computed from real section using what I showed you earlier, or backbone curve, idealized curves given by various design codes. Either way, moment curvature curve, moment rotation curves are essential for using the determination of this. If we use the fiber hinge, once again, program will use the same concept. It will determine the moment curvature on the fly. So moment curvature curve, whether we use the lump plasticity or fiber hinges, are still essential. So we can use this realistic determination of the capacity, deformation capacity, to link it to the MCE, and thus determining direct correlation between actual expected loading and actual expected strength without any factors in between. So let's look at one example now. So let's say we have a frame like this with given column and beam reinforcement. And if I use this frame as an elastic analysis, linear elastic analysis, apply the load, get the D, then you can plot this versus the reaction, which is the base shear. Then we can plot the base shear versus the roof displacement, and you get those plots. So the light blue is a plot using constant gross cross sections. Dark blue is a plot using reduced or cracked cross section, but still using linear. And this can go forever. And you can see here that according to this linear analysis, this frame can carry up to 4,000, 40,000, or 50,000 kilonewton of force. But in reality, if you put the nonlinearity into this one and bring in the actual frame dimensions, reinforcement, confinement, and everything, and create the proper model from this one using the interaction curve, get the load capacity from there, moment curvature curve for different axial loads, put them back into the moment curvature relationship, and then for beam and column, both of them, you determine the moment curvature relationship, put it back as a moment rotation, carry out a pushover analysis, nonlinear, then you will see, so using this diagram, you will see now that the nonlinear capacity will drop. And the frame cannot even carry 5,000 kilonewton, unlike the 40,000 predicted by linear analysis. And if you include the P delta effect, it will be even less. So if you put them all together and just look at a small range of the frame, you can see from here that at a drift of 0.5%, you will get a force factor of 1. That means linear and nonlinear are the same. But as we go higher deformation, then linear and nonlinear have a ratio, in this case, of 3. And if you go to even higher deformation, the linear and nonlinear have a ratio as large as 8. This is typically reflected in R factors and omega factors. So that's how the linear versus nonlinear capacity will vary. And we are now having a tool to determine the nonlinear capacity because we have gone from the material to curvature, to rotation, and to displacement. So if you use the same thing in a large structure, do the same, then we can see that you can determine the stress state and various state and damage state in a structure by going through the pushover curve while monitoring the curvature, strain, and stresses. So that means it can give you a full picture of the structure response as the load progresses from 0 to the maximum. And that's what the benefit that we have talked about. So let's conclude now. Strength design only addresses one of the overall design objective, which is strength, which is also arbitrary in the sense that the loads are multiplied by a factor, so the load is not real, and they are combined using different combination factors. and that the capacity is reduced by capacity factors, which is also not real. So for the strength to work, we are on an arbitrary code-based controlled strength state to ensure that the structure is safe in certain definition. But moment curvature and corresponding derivations can give us almost all the quantities that we need. Even to some extent, it can give us a damaged state, as we have seen when the concrete is gone and steel is yielding. So with that, I would like to thank everyone